In the last class, we discussed the various forms of differential equations. In ordinary differential equations category. Okay. In ordinary differential equations category, we had discussed the solution of differential equations in totally four methods or four forms of differential equations, of which we discussed three. So first is separation of variables, that is the most fundamental. Then homogeneous differential equation, where we can convert the differential equation to y by x form or x by y form, and then substitute y by x by u, and then after that it converts to a separable variables form. Then we discussed linear differential equations. So and today we'll continue with linear differential equations and go with exact differentials. So yeah, so in linear differential equations, as we discussed in the last class, the linear differential equations, the solution, the differential equation is of the form dy by dx plus px, p of x times y is equal to q of x. The dependent variable and its derivative, they appear in degree 1 and they're not multiplied together. So that is the definition of a linear differential equation. So y and dy by dx both will have degree 1 term. They will be of degree 1 maximum, and they will not be multiplied together. Functions of x, p of x and q of x can be anything. It doesn't matter. But this is the differential equation. The solution of this differential equation is multiply by the integrating factor. Integrating factor times y is equal to integral of integrating factor times q dx plus c. Now the integrating factor is e power integral p of x dx. So, and the same thing, if it is the x is the dependent variable and y is the independent variable, then it changes. Dx by dy plus p of y times x is equal to q of y. So x is the dependent variable. The dependent variable and its derivative appear in degree 1 and are not multiplied together. So this becomes the linear differential equation. Now this linear, the solution to this linear differential equation is integrating factor times x, in this case the dependent variable, is equal to integrating factor times q dy plus c, and the integrating factor is integral of p of y dy. So similar, and we did a few problems on linear differential equations in the last class, 2 problems in fact. So okay, let's do some more of it. Two more problems we'll do. After that, we'll move on with further. This is very important. You get a lot of questions on differential equations of first order, first degree. Although this is before, um, during the intermediate level or the class 12th level, we do this. However, um, because it's fundamental, this question is asked repeatedly. So we have done two problems. Now look at this one, third. Solve dy by dx is equal to y upon 2x log y plus y minus x. Now this is not in a polynomial form. It is in fraction form of y and x. So how do we solve this problem? What we need to do, just take the reciprocal and see how it looks. Dx by dy is 2x log y plus y minus x by y. Okay. So now dx upon dy is equal to 2, take x common, 2 log y minus 1 upon y sorry, this is made a mistake here. This is 2y. This makes sense here. This is 2y. So what we get is 2 log y plus 1 minus x upon y. Take this to the other side. So we get dx upon dy plus x upon y is equal to 2 log y plus 1. So this is of the form dx by dy plus p of y times x is equal to q of y. So p of y here is 1 upon y. Q of y is 2 log of y plus 1. So solution is integrating factor times the dependent variable. So first find the integrating factor. The integrating factor e raised to integral of p of y dy. So e raised to the power 1 upon y dy, which is e raised to the power log y, which is equal to y. So integrating factor is y. Therefore, the solution is integrating factor times the dependent variable is equal to integral of integrating factor times q plus c. So now integrating factor is y times x is integral of y times 2 log x, 2 log y plus 1 dy plus c. So of course, y log y. Let us do this. This is integral of 2y log y dy plus integral y dy plus c. This will integrate by parts. In I late, inverse, logarithm, then algebraic. So logarithm will be the first function, algebraic will be the second function. So integrating by parts, I'll write here. Okay. So first function into integral of the second. The second is 2y. Integral of 2y is y square minus integral of the derivative of the first 1 by y into integral of the second. And here, okay, we can leave this integral of y dy plus c. Now what's happening here? These two get cancelled. This is integral y with a minus sign and integral y with a plus sign. They are getting cancelled. So what we get is y times x is equal to y square log y plus c. Therefore, the solution is x is equal to y log y plus c upon y. This is the solution. Okay. So this was not directly in linear form, but upon conversion, it came to a linear form and then we solved. Let us do one more problem. This is finding the particular integral, that is a particular solution. So solve cos square x dy upon dx minus y tan 2x is equal to cos to the power 4x, where conditions are given. Mod x is less than pi by 4. That is, x lies between minus pi by 4 and pi by 4. And y at pi by 6 is equal to 3 root 3 upon 8. So now the equation is in this form. We have to get it in the standard form. To get in the standard form, dy by dx doesn't have a coefficient. So divide throughout by the coefficient of dy by dx, that is cos square x. So we get dy upon dx minus we get y times tan 2x secant square x is equal to cos square x. So this is in the form dy by dx minus, sorry, plus P of x times y is equal to Q of x, where P of x is minus tan 2x secant square x, and Q of x is cos square x. So now this is a linear differential equation. Now the integrating factor is e to the power integral p of x dx. Now let us evaluate this integral p of x dx. This is integral minus tan 2x secant square x dx. So this is minus integral 2 tan x by 1 plus tan square x. 2 tan x by 1 plus tan square x. This is tan 2x. It is sin 2x upon cos 2x. So it's a minus sign. Oh, it's a minus sign, yeah. 1 minus tan square x times secant square x dx. Okay. 2 tan x upon 1 minus tan square x. Now, this substitution put tan x is equal to t. This gives us secant square x dx, differentiating is dt. So this integral we get is integral 2t by 1 minus t square dt. Taking this minus 2t inside, this minus sign inside. Now what we get is the numerator is the derivative of the denominator. This is f dash t upon f of t, which will be log mod 1 minus t square, which is log mod 1 minus tan square. Now, given that, important, x lies between minus pi by 4 and pi by 4. That means the values of tan x will lie between minus 1 and 1. So it will be less than 1. So tan square will lie between 0 and 1. In that case, 1 minus tan square will be a positive quantity. So this will only be log of 1 minus tan square x, since mod x is less than pi by 4, which implies tan x lies between minus 1 and 1, which further implies that tan square x lies between 0 and 1. It can take the value 0. So because of this, we can remove the modulus sign. So this is integral p dx. So what is the integrating factor? Integrating factor is e power integral p of x dx. So this is e power log 1 minus tan square x, which is 1 minus tan square x. E power log of something will be the same number. So this is the integrating factor. Now the solution. So y times the integrating factor. Therefore, this solution is y times the integrating factor, or integrating factor times y is equal to integrating factor time integral of integrating factor times q plus c. So we have y into 1 minus tan square x is equal to integral of 1 minus tan square x times cos square x dx plus c. So when we multiply, we get integral of cos square x minus sine square x dx plus c. Multiplying cos square inside. This is integral cos 2x. And integral of cos 2x is sine 2x upon 2. We can simplify further. Now, there is a given condition. Now, given that at x equal to pi by 6, y value is 3 root 3 upon 8. So substitute. Therefore, to find c, basically, when this condition is given, it means we have to find a particular value or the particular solution of the differential equation. So y is 3 root 3 upon 8 times 1 minus tan square pi by 6 is equal to half sine twice of pi by 6, that is pi by 3 plus c. Now tan 30 degrees, tan pi by 6 is 1 upon root 3. Square will give us 1 upon 3. This is half times sine 2 times 30 is sine 60 root 3 upon 2 plus c. So we get 3 root 3 by 8 into 2 upon 3 minus root 3 upon 4 is equal to c. So here 3 cancels and 2 cancels this 4 times. So root 3 by 4 minus root 3 by 4 is 0. This implies the constant is 0. Therefore, the particular solution y times 1 minus tan square x is equal to half sine 2x. Or in other words, writing it differently, y is sine 2x upon 2 times 1 minus tan square x. So this is the solution. So it's a very important integral linear differential equations. We get these are some problems that are involved integrals. I gave on purpose, but the questions that come in GATE are little simpler side on integration part, but I've given a little tougher side so that you get some good practice. Now, in this category, type 3B. Now, integral is not linear differential equation straight away, but it is reducible to linear differential equation. reducible to linear differential equation. So there are different types. The first form is called as the within this there is type 1 or case 1. This is the Bernoulli's equation. Bernoulli's equation uh, is of the form dy by dx plus px times y is q of x multiplied by y power n. So this is not a linear differential equation. So here n should not be equal to 0 or 1. If n is equal to 0 or 1, then this we will not be able to simplify this. Now, this is not a linear differential equation. Why? Because the dependent variable is not only appearing in degree 1, it is appearing in degree n. The dependent variable has a degree n, not degree 1. So how to deal with this? So the way to deal with this is, so approach to this problem. Divide throughout by y power n. If we do this, what do we get? 1 upon y power n dy by dx plus p of x times 1 upon y power n minus 1 is equal to q of x. Now substitute 1 by y power n minus 1, this term as u. Okay. So this implies y to the power 1 minus n is u. Now when you differentiate, we get 1 minus n to the power y, 1 minus n into y to the power, y raised to the power 1 minus n minus 1 dy, differentiating, is equal to du. Okay. So what we get is so if we differentiate with respect to x, both are functions of x. So this also implies that 1 minus n into y to the power minus n dy by dx is equal to du by dx. So 1 upon y power n dy by dx will become equal to 1 upon 1 minus n du by dx. So let us substitute this in this equation. So this is 1. So substituting the above in 1, we get 1 by 1 minus n du by dx plus p of x times u is equal to q of x. So we can simplify further. P of x into 1 minus n times u is equal to q of x into 1 minus n. So this together you should take as p. This together you should take as q because you have just multiplied this by a constant. Okay. We cannot write this as p bar as this function and this as q bar. Okay. So now this is in the above is a linear differential equation. This is a linear differential equation because the dependent variable u and its derivative appear in degree 1 and are not multiplied together. So this is du by dx times p of x times u is equal to q of x, that form. So the solution is integrating factor times u is equal to integral of integrating factor times q. This time q will be q of x into 1 minus n dx plus c. Now the integrating factor is e raised to the power integral of p of x into 1 minus n dx. So this is the solution. So when this particular form uh, is called as the Bernoulli's equation in differential equations. So when you get qx into y power n. Now we can, other type may be there, another type of differential equation. So equation of the form f dash y dy by dx plus p of x times f of y is equal to q of x. Now this is some function of y and this is the derivative here. So here equation of this form method approach is like this. Substitute f of y is equal to u. Then f dash y du by dy by dx is equal to du upon dx. F dash y dy by dx is equal to du by dx. So this implies du by dx plus p of x times u is equal to q of x. All right. This is a linear differential equation which can be solved. Okay, these are the two methods, two approaches for linear differential equations. So we need practice to solve problems of this type. And I'll be just sharing you a question set right after this class where you should be able to solve. So let us take examples. Solve dy by dx minus y tan x is equal to minus y square secant x. So here we see dy by dx minus y tan x, first of all, and we have minus secant x times y square, y power n. So what should we do? Divide by y square. So 1 upon y square dy by dx minus 1 upon y tan x is equal to minus secant x. Now substitute minus 1 by y is equal to u, because you have to get a plus sign here. So minus 1 by y is plus u. This gives us differentiating minus of minus 1 by y square dy by dx is equal to du by dx. One by y square dy by dx is du by dx. So this implies du by dx plus u tan x is equal to minus secant x. So this is a linear differential equation form. This is a linear differential equation. Therefore, integrating factor. What is the integrating factor? E power integral of p of y dy, p of x dx. So e power log mod secant x, taking the positive values, you can just write log secant x. So it is secant x. Integrating factor is secant x. So solution is u. Later on we'll write u as in terms of y. Now u times the integrating factor is equal to integral of integrating factor times q. So we get u secant x, integral of secant square x is tan x, derivative of tan x is secant square x, so integral of secant square x is tan x plus c. Multiplying throughout by cos, we get u is equal to minus sin x plus c cos x. Now u, what is u in terms of y? Is minus 1 upon y. Mhm. Minus sin x plus c cos x. So multiply by y minus 1 and take a reciprocal 1 upon sin x minus c cos x. This is the solution. So this was the example of Bernoulli's equation. Let us do one more of another type. Solve dy by dx is equal to e power x minus y, e power x minus e power y. So we just have to do manipulation. When we get an equation, we don't know whether it is variable separable, linear differential equation or what, but by hit and trial, you should see how it is. So let me put this e power y this side or multiply by e power y. We get e power y dy by dx is equal to e power x into e power x minus e power y. Okay. This we can further simplify e power y into dy by dx plus take this to this side e power x into e power y, e power x the whole square, that is e power 2x. Now we can substitute, now directly it is not in linear form, but we can substitute e power y as u. When we do e power y as u, what happens? Differentiating, we get e power y into dy by dx is du upon dx. So we get du upon dx plus e power x times u is equal to e power 2x. Now this is a linear differential equation. Integrating factor is e power integral p of x dx. So we get e power x. Now solution, integrating factor times u is equal to integral of integrating factor. Or integrating factor is e power x. E power x into e power 2x. So here we need to substitute, put e power x as t. This implies e power x dx will be equal to dt. So this e power 2x can be written as e power x into e power x. So this integral becomes integral e power t into t to e power x dx becomes dt. So integrating by parts, first function will be t, second function will be the integral minus integral of the derivative of the first, that is 1, integral of the second. So we get t e power t minus e power t plus c. Therefore, we get u times e power x is equal to e power x, t is e power x times e power x. One second. E power t we can take common, e power x into e power x minus 1, t minus 1 plus c. What was u? E power y. So first let us do this. U is e power x minus 1. We are dividing c into e power minus e power x. e power y is e power x minus 1 plus c times e power minus e power x. So this is the solution. So one is of one type, another is one was of Bernoulli's equation form, other was a um, by substitution form. One more. This type is very frequently we can get it. Solve x y square dy by dx minus 2y cube is equal to 2x cube when hmm, given that given that when x equal to 1, y is equal to 1. When x equal to 1, y is equal to 1. Sure. So let us start. Shall I give you time to solve this? I'll give you 3 minutes or 4 minutes to solve. Just attempt this. Okay, any answers? Anyone close to? You can raise hands. All right, please complete. You can put the answer in the chat. Okay, I'll proceed with the solution. Yeah. So we can observe this, how the equation is. This is y cube, this is y square dy by dx. So we can substitute in this. This is the given differential equation. Substitute y cube as, say, u, which implies 3y square dy by dx will be du by dx. 3y square dy by dx is equal to du by dx. So, which implies y square dy by dx will be 1 by 3 times du by dx. So, therefore, the differential equation becomes in the form x times 1 by 3 du by dx minus 2u is equal to 2x cube. So multiply by 3 by x throughout. So this implies du by dx minus 6 upon x times u is equal to 6x square. So multiplying with 3 upon x throughout to get it this form. So this is of the form du by dx plus p of x times u is equal to q of x, where p of x is equal to minus 6 upon x and q of x is equal to 6x square. Therefore, the solution, integrating factor is e power integral p of x dx, e power integral minus 6 upon x dx, which is e power minus 6 log x, which is e power log x to the power minus 6, which is x to the power minus 6. This is the integrating factor. So this implies, therefore, the solution is u times the integrating factor is equal to integral of the integrating factor times q, that is 6x square in this case here, So what we get is u into 1 upon x power 6 is 6 integral 6 upon x power 4, which is 6 into x to the power minus 5 by minus 5. No, we are integrating, not differentiating, sorry. Minus 4 plus 1. So x to the power minus 3 upon minus 3. So throughout multiply by x power 6, we get u is equal to minus 2 x cube plus c x power 6. So what is u? Is y cube. This implies y cube is equal to minus 2x cube plus c x power 6. Given that when x equal to 1, y is equal to 1. So 1 is equal to minus 2 plus c into 1. So c is 3. Therefore, we get y cube is equal to minus 2x cube plus 3x power 6. This is the solution. This is the solution of the linear differential equations. Good. So I spent a lot of time on linear differential equation on purpose, because linear differential equation of single degree 1, order 1 is very, very important. Very important. Next is exact differentials. In this type, the fourth form see, exact differential, simple definition I'll give you. Suppose we have 3x square dx. We can write this as d of x cube, right? So this term we can say is the exact differential of x cube. So what we get in differential equation, the whole differential equation is an exact differential. For example, x square y cube, let's say, we get x square into 3y square dy plus 2x y cube dx. So let us say we have this equation 3x square y square dy plus 2x y cube dx is equal to 0. Let's say now we get an exact differential here. This, how to get to the exact form, we will see later, but this is an exact differential. This is exact differential. That means we can write this as d of x square y cube. How to get to this form, that we will study soon, is equal to 0. So solution is x square y cube is equal to c. this is the solution of this differential equation. This is the differential equation. This is in the exact form. So exact differential means you can write the whole differential equation into one differential. That is the idea. So now formal definition. Now consider a function. So consider a function u of x and y. Now then du is dou u by dou x times dx plus dou u by dou y times dy. So this implies du by dx we can write as m dx plus n dy. So this form m dx plus n dy converts to du when where dou m sorry where where m is equal to dou u by dou x and n is equal to dou u by dou y. Okay, so we have considered a function u of x comma y. That u, when we do a differential of u, the total differential is dou u by dou x times dx plus dou u by dou y times dy. So we replace this with m and this with n. So we have just written this in this form. Now we know since dou square u by dou y dou x is equal to dou square u by dou x dou y, we get, what did I do? Differentiate dou u by dou x by partially with respect to y. So I get dou m by dou y is equal to dou n by dou x. So from this, we can get an conclusion that when can a function like this m dx plus n dy, when can it be called as an exact differential? So like this. So if dou m by dou y is equal to dou n by dou x, this m dx plus n dy can be written as du. So based on the above, exact differentials are defined as follows. So this is the formal definition. An equation of the form m function of xy dx plus n, which is a function of xy dy, equal to 0, is called an exact differential if, what is I double f means, it is double implication, forward implication and backward implication. That means, I'll just explain that. If dou m by dou y is equal to dou n by dou x. This is the definition of the exact differential. What it means is, this if, double if means m dx plus n dy will be called as an exact differential if this condition holds. Said in the reverse manner, dou m by dou y is equal to dou n by dou x will imply this condition, if it holds true, it will imply that m dx plus n dy is an exact differential. So how to solve? All right. The solution is like this. So now solution lies in finding the function u such that u is equal to m dx plus n dy. Now, where m is equal to dou u by dou x. So, which implies u is equal to integral of m with respect to x. This is partial, treating y constant. Okay, this is y constant. So, plus this will be a function of y. Now, how do you find this p? Differentiate. Now, n is equal to dou u by dou y. So, differentiate this with respect to y. Okay, and from this find p. The easy way to do it, there are tricks to do it. I will explain the tricks also. Now, alternative is solution is u is equal to c. U is equal to c. M dx plus n dy equal to 0. That means u is equal, du is equal to 0. So solution will be u is equal to c. Now u is integral m dx plus integral of terms of n not containing x. Terms of n not containing x times dy is equal to c. This is a recommended alternative solution. Okay, you get integral m dx, but then what are these terms? Which this purely a function of y. So terms which do not contain x, and then integrate that, you will get this terms p of y. So there's a But then by careful observation, we can write exact differentials, but we'll take a few problems. Solve x square minus ay dx plus y square minus ax dy. Now solution to check whether it's exact or not is m is x square minus ay. N is y square minus ax. This implies now dou m by dou y is equal to minus a. Dou n by dou x is equal to minus a. Now since dou m by dou y is equal to dou n by dou x, the given differential equation is an exact differential. It's an exact differential. So you can convert this to d of u. So how to do this? So u is integral of m dx plus integral of terms of n not containing x dy. So integral of m is x square minus ay dx plus integral of terms of n not containing x is only y square dy. So we get x cube upon 3 minus axy plus y cube upon 3. Therefore, solution is u equal to c. Because this mdx plus ndy, now this mdx plus ndy equal to 0, because it's an exact differential of u, it becomes this. Therefore, the solution is, when you integrate this, we get u equal to constant, which implies x cube upon 3 minus axy plus y cube upon 3 equal to 0. Now this is once you know this is an exact, I'll give you an alternative, which is much easier than to remember this. Of course, you can remember this by logic and solve it. That is not an issue. Alternative. I prefer this one, this method. Now, x square minus ay dx plus y square minus ax dy is equal to 0. Okay. Now this is the alternative. Once we know that this is an exact differential, this is an exact differential, because dou m by dou y is equal to dou n by dou x. Dou m by dou y is equal to dou n by dou x. Okay. So now, once this is exact, see what I do now. Therefore, I'll split this. We can write as x square dx minus a y dx plus y square dy minus ax dy. What I do, I'll write this x square dx. Now, minus of a I take and write y dx plus x dy plus y square dy. So here x square is related to dx. So I can always write this is differential of x cube upon 3. I integrate this. X square integral is x cube upon 3. So this term x square dx is a differential of x cube upon 3. Now this is y dx plus x dy. It is same as the differential of applying UV rule. This is x dy. Derivative of first function, keeping second as it is, that is y dx, plus keeping first function as it is, derivative of the second. So UV rule. So y dx plus x dy. And this one will be differential of y cube by 3. So once I know that it's exact, I'm sure that it will converge to a single differential. So this becomes differential of x cube upon 3 minus axy plus y cube upon 3 is equal to 0. Therefore, the solution is very simple. Integrate this d of this whole thing. So with respect to itself. So upon integration, we get x cube by 3 minus axy plus y cube by 3 is equal to c. Clear? Clear? If it is clear to you, please raise your hand. This step the way I did it. Please give a hand raise so that I know that you understood it. Okay, none of you understood it. So then please ask a question. Which part you did not understand?
Sir, actually, the step from where you are taking the D in separate columns to the final step, I did not understand.
Which one? This one.
This, yeah, yes, sir.
From this to the next.
Yes, sir.
No, this is simple. Na? Derivative of sum of functions. What is d of f plus g? It is df plus dg. So from here, I'm going back. That's all.
Oh, okay, sir. Yes, sir. I understood.
Right. Any other question? None of you raised hands. That means everybody has a doubt. So please raise. Please speak out your doubt. Don't feel shy. Where did you not understand? See, this is an exact differential. Means I can convert. This is a total derivative of a single function. So I have to arrive at that single function. This is this expression, the single expression. How to do? I went step by step. This is x squared dx. I separated. Y dx I separated. Y squared dy, x dy. This has coefficient of. Now I split. X squared dx I write as it is. Y squared dy I write like this. This one I take minus a common and y dx plus x dy. Now this term is d of x comma x into y. You will get x dy plus y dx. So that's what it is. And this term is differential of x cubed by 3. This is differential of y cubed by 3. So sum. These are differential of each terms. That means this is differential of the total. X cubed by 3 minus a xy plus y cubed by 3 equal to 0. So then when we integrate it, we get this solution. It's the exact differential. Yes, any more question?
Sir, one more question.
Hmm.
Sir, in this case, the backward mapping is like you took x square and you backward mapped it to x cubed by 3. It is
Yes.
easy. But now if suppose it is something log type of function, then
So
will
you
back.
just have to integrate it.
Oh, even in the multiple time, then we'll have to do integration by parts.
No,
In the middle
no,
term.
no. You have to observe for pairs. By observation, you will know. This was a simple question. That's why I showed it this way. This is a very simple one. I'll give a log example
Okay, sir.
right now. Okay. See, by this also we got the solution. Integral m dx plus integral terms of n not containing x dy plus c. Same thing we got. But you will have to remember this, na? Suppose you forget. Then you are stuck. How do you solve? By simple common sense logic, you can solve this. I prefer this method than by mugging up so many methods. Try this one. Solve 2x log y dx plus x square upon y plus 3y square dy equal to 0. Okay, I will write the solution for this in 5 seconds, just seeing it by practice. That is, it is not that I remember this problem solution. As I'm writing, I know what the solution is. So I want you to solve this and tell me the answer. I'll give you 1 minute's time only, not more. Anyone who got the answer, please raise hand. Good. Good. Two solutions. Two of them you have solved. Good. Okay, I'll do by, um, we can check, I'll solve now. Now this is mdx plus ndy form. Now dou m by dou y will give us 2x into 1 by y, partial derivative with respect to y. So 2x by y. Now dou n by dou x, differentiating this partially with respect to x, this term becomes 0. This is 2x upon y. So dou m by dou y is equal to dou n by dou x. Therefore, m dx plus n dy must be equal to some du, an exact differential. There's an exact differential du. So I have to find this u. Okay. So u basically is m dx plus n dy. All right. We'll come back to this. Dou m by dou x times dx plus dou, oh sorry, dou u by du is m dx plus n dy is dou u by dou x dx plus dou u by dou y dy. Now let us look how to solve. Now I do by method 1. This is by inspection. This is, I'm using my intuition to solve it. I'll do it very fast by this. 2x log y 2x log y dx plus x square upon y plus 3y square dy. So now this is y, treating y as constant. I'll write this as log y times 2x dx. Now this is y, I'll write as x square into dy upon y, the second term. And this one 3y square dy. So I get this as log y. This is differential of x square. I integrate 2x, I get x square. So differential of x square is 2x dx. And x square times dy upon y. I'll get differential of log y here. Derivative of log y is 1 by y times dy. So differential of log y is 1 by y dy plus differential of y cube is equal to 0. Okay. So this implies this. Now, this is UV rule. U derivative of V plus V derivative of U. This is UV rule. So I will write as this is differential of x square log y plus differential of y cube. Now using this sum rule for differentiation, you will get x square log y plus y cube. So solution is, now you integrate. Solution is x square log y plus y cube is equal to c. Okay. This is a method by inspection. Now other method, this simple. And I said I prefer this one. Now method by integration. So du is m dx plus n dy, which is dou u by dou x dx plus dou u by dou y dy. What we want is, we want to find u, right? So u by the formula, I'll do with the formula, without the formula. Now u, okay, I'll do without the formula. Take this, dou u by dou x is equal to m. So we get u is equal to integral m dx plus a function of purely in terms of y. Because when you do a partial derivative with respect to x, this term should be 0. So we get u times, what is m? M is this term, 2x log y, integral of 2x log y dx plus p1. So we get, treating y as constant, you get integral of 2x is x square log y plus p of 1. So I use this, dou u by dou x is equal to m. Now dou u by dou n, dou u by dou y is equal to n, which is x square upon y plus 3y square. X square upon y plus 3y square. Now we have found u up to here. Okay. So differentiate this u with respect to y. So you will get x square upon y plus p dash y purely in terms of y dp by dy is equal to x square by y plus 3y square. So this cancels. So from here we get p dash y is equal to 3y square, which means p of y is equal to y cube. Integrating. So what we get is u, therefore u is equal to x square log y plus y cube. And what is the solution? U is equal to constant, which means x square log y plus y cube is equal to constant. That's what we got from here. X square log y plus y cube equal to constant. Alternatively, that formula we can apply, integral of m dx plus integral of n, omitting the terms containing x dy. So when you do that, terms containing, directly you get this term x square log y plus y cube equal to c. All right, this is exact differential. Now I'll give you some tricks. Now they may not be directly exact, but you can reduce to exact. Of course, at this depth, I'll give some simple problems. And gate, you don't get questions at this depth unless it is very simple. Gate, actually questions are reasonably simple in Gate. Just that it should strike you. Just the volume of the syllabus is large in Gate, but the type of problems you get is easy. I will, in the next class, that is tomorrow's class, I'll make you do some problems on this. Reducible to exact differential. Now, sometimes, so let's say if m dx plus n dy equal to 0 is not an exact differential, then it is possible that upon multiplying by an integration factor or integrating factor. Now, this integrating factor we don't find like the linear differential equations. Multiplying by an integrating factor, it can be reduced to an exact differential. For that, so there is no definitive method. You have to do by inspection. The following differentials will be useful to identify the integrating factor. By inspection. Inspection means just by observation. There's no hard and fast rule. So some of these I'll give you. There's a big list, but I'll not go through the whole list. Suppose dx plus or minus dy is there. This is differential of x plus or minus y. Simple. Now we already did this, x dy plus y dx. This is the exact differential of xy. Now how about this? Y dx minus x dy upon y square. This is u upon v rule. So this is differential of exact differential of x upon y. And the same thing if it is x dy minus y dx upon x square, this will be the exact differential of y upon x. Again, you can apply u by v rule, split it into two, 1 by y dx minus x into dy by y square. So you can convert and bring to u by v. But or just remember the u by v rule of differentiation. Now, if we have x dx plus y dy, the integral will be x square by 2, y square by 2. So this is the exact differential is half of d of x square plus y square. So left hand side, the exact differential of half of d of x square plus y square. This is easier, like dx plus dy upon x plus 1. This will be the exact differential of log of x plus 1. 1 by x plus y into differential of x plus y. So that's what we get. So these are some interesting differentials which will help us. X dy plus y dx upon xy. Numerator is d of xy by xy. So this will be log of xy. So like this, we can do, there are many such differentials. Let's do one or two examples. There are few more little complicated ones I'll give you. Y dx minus x dy upon x square plus y square. Wow. So what will be this one? This immediately you cannot predict. You will have to write steps. Divide by y square. If you divide by y square, I'll get y dx minus x dy upon y square by x by y the whole square plus 1. This will be equal to d of x by y. The numerator is d of x by y. Just now we did here. Y dx minus x dy by y square will be d of x by y upon x by y the whole square plus 1, which is tan inverse. If you integrate this, integral of dx upon x square plus 1 is tan inverse x. So this is tan inverse x by y. This is a differential of tan inverse x by y. So this is the answer. Immediately you will not be able to think about it, but this is how you do it. By these steps. So similarly, x dy minus y dx by x square plus y square is equal to d of tan inverse y by x. All right, exactly like that. So let's do some problems. There are many. You can keep writing so many if you wish. Another 10, 20 we can write combinations. So let's do this. Solve x dx plus y dy is equal to x dy minus y dx. Now these are the left hand side is an exact differential, d of x comma y, sorry, half of uh, half of differential of x square plus y square. This is an exact differential. This is not x dy minus y dx. If it was plus, it was an exact differential. Now you can cross check and see. Here you get x plus y dx, and this is y minus x dy. If this is m, this is n, so dou m by dou y is equal to 1, dou n by dou x is equal to -1. So not exact. It is not an exact differential. Okay. So what is the alternative? How to solve it? Now you look into all these expressions. If I multiply a factor, then this should become exact differential. This should become exact differential. So look at this. X dx plus y dy. So, but here you see y dx minus x dy, x dy minus y dx. So either, so I have x dy minus y dx. I can divide by y square. If I divide by y square, this will not help me. So x dx plus y dy is equal to x dy minus y dx. So what I get here is half d x square plus y square. This is as it is. Now I should multiply or divide by this factor which contains x square plus y square. Go up, you can see this. I have this term x square plus y square. So divide throughout. So your integrating factor multiplied throughout by 1 upon x square plus y square. This will be the integrating factor. This is the integrating factor. What happens? You just see half d of x square plus y square upon x square plus y square is equal to x dy minus y dx upon x square plus y square. So this is half log derivative of log x square plus y square. And this one is just now we did derivative of tan inverse y by x. Because you can write it in two steps, divide by y square, divide by x square, and you get d of y by x by 1 plus y by x whole square. So now integrate, you get the solution. So you got this as the exact differential. So integrating, we get half log x square plus y square is equal to tan inverse of y by x plus c. Okay, so this is the solution. So this is the way we use the integrating factor for exact differential. Okay, I'll end here. I'll share some problem sheet, and also I tomorrow I will make you solve some important problems from previous gate papers. So I'll share this notes with you right now. So immediately you can go through it and come prepared for tomorrow.